this chapter, we will be exploring the calculus of trigonometry. In this lesson, we will be looking at applications of trigonometry. In this case, the specific application we're interested in is curve sketching.
All right, everybody. So now we're going to do an application of derivatives in trigonometry. We're going to do curve sketching. We've already done a bunch of this before, but now we're going to do a trigonometric function here. And we're going to walk through all the same steps here. Now, one of the things I'll say before I get into this is normally would be the type of guy that would prefer fractions and exact values, so like square roots and whatnot in my answers. But we're going to be sketching this, and to be honest, I don't have a really good clean view of where the square root of 2 is on the grid, where pi should be and stuff like that. All I'm trying to say here is that in this particular case here, it does make more sense to get decimal answers because they're going to be much easier to place on the grid when we get to that point. So, having said that, what I'll do here is, as we walk through this, when it comes to that point here, just know that that I've done this on the calculator already and I've got the answers here. So some of these things I'm going to move through a little bit quicker than normal, mostly because I've done the calculations beforehand. So, to start off with, the very first thing that we want to look at here is going to be our domain. And actually, in this particular case here, that's done for us. The domain is given to us right here. We're trying to sketch y equals the sine of x plus the cosine of 2x between 0 and 2 pi. Well, I've already got that. Okay, I already know that the domain that I'm working on here is from 0 to 2 pi. Now, is there, however, anywhere in there where this would be undefined or give me some sort of problems? Nope. Nope. Sine is defined for all real numbers. Cosine is defined for all real numbers. The sum of them should be. That shouldn't be a problem here. So there we go. So between 0 and 2 pi, all real values in between there. Good. Next thing we're going to look at here are the intercepts. Okay, and I'm lazy. Let's start with the y-intercept. We'll grab the low-hanging fruit here first. Now, to get the y-intercept is pretty straightforward. We simply make the independent variable equal to 0, and that simply means making x equal to 0. Well, the sine of 0 is going to be 0, not a problem. 2 times 0 is 0, and the cosine of 0 is just going to be 1. So the y-intercept here will be 1. And remember, I want to write it like this. I want the y-intercept to be equal to 1 here. I don't want to leave it as y equals 1 because I'm asking you for the point where this graph crosses the y-axis. If you state y equals 1, you're not giving me a pointer or a number. You're giving me another equation, another line, y equals 1. In this case right here, when I ask you for the y-intercept, I'm really asking what is the y-coordinate when the x-coordinate is equal to 0. Okay. So answering it like that is just fine. Just say, yeah, the y-intercept is 1. Now, let's take a look at the x-intercept. This is going to be a little bit more complicated, and that's simply because anytime you're looking for the x-intercept, you're solving an equation. So we're going to set y equal to 0. And this will be the sine of x plus the cosine of 2x. Okay? Well, that's an equation now that I have to solve. Up here, it's just evaluating. I just plug in a 0 and get the answer. Here, not quite so straightforward. So I'm going to have to do a little bit of work here. One of these is going to have to change, and it's very likely got to be this one right here because of the 2x in it. Okay? So I see the cosine of 2x, and I know that there are 3 different identities that go along with the cosine of 2x, but only one of those is just in terms of sine, and that's this one, 1 minus 2 sine squared of x. So that's the one that I want to use because now I've got an equation that's just in terms of sine. Yeah, I think what I'll do here is I'll factor out a negative. That'll get me negative, and I'm going to bring the quadratic term forward here. 2 sine squared of x minus the sine of x minus 1. Okay, and it turns out I can factor that. So 2 sine of x sine of x. My product here has got to be equal to -1, but the sum's got to also be equal to -1. That will happen so long as it's 2 times -1 over here, and then I add the 1 right there. So this is going to happen. I will get x-intercepts wherever the sine of x is equal to -1/2 or the sine of x is equal to +1. Okay, so now to solve this here, I would go through a little bit of a procedure. The expectation is that you've done this before, okay, that you've seen this before, so I should be able to jump really quite quickly to the answer here. I know, for example, that because this is negative, I'm going to have answers in the third and fourth quadrants. I would find my reference angle by doing the inverse of 1/2. That's going to get me pi/6. And when I put those into the two quadrants here, I'm going to get 3.7. Now I'm rounding this to the nearest tenth because if I go any further than that, I'm not going to be able to plot that. Okay, so 3.7, I can at least get a really good sense of where that is. And then 5.8 will be my fourth quadrant angle. Over here, where does sine go to 1? Well, the answer is pi/2. But again, I don't have a really good sense of that unless I've got my x-axis marked off in terms of intervals of pi, fractions of pi here. So what I'm going to do here is I'm just going to give it to us, or to you, in decimal form. That's going to be 1.6. Okay, that's my pi/2. So there's my y-intercept, and I've got 4 x-intercepts. And bear in mind, I'm solving this within the domain that I'm given. I know that these repeat, okay? Sine of x is equal to -1/2 for an infinite number of values. So is sine of x equal to 1. But I'm only looking for the values between 0 and 2 pi. So now, 3, let's take a look at symmetry. Now, this really isn't going to be that big of an issue for us. Whoops, sorry, you can't see that. Mostly because my domain isn't symmetric about the origin. I am from 0 out to 2 pi, so it doesn't really even matter what the symmetry is, but let's just take a look at it anyway. If I plug -x into this, that will become the sine of -x plus the cosine of 2 times -x. Well, sine of -x, sine, and you should have seen this before here, sine is an odd function, so I can pull that negative out. And there's reasons for that that we could go into in a different context, maybe not right here. But cosine, 2 times -x would be -2x. Cosine is even though, so that negative actually just kind of disappears there. And so what I'm left with is a function that is not equivalent to the original, so it's not even, but at the same time it's not the same as the original with the negative factored out. So as a result here, this is neither, okay, odd nor even. So there's no symmetry the way I would like to see the symmetry there. And that's okay. That's fine. Let's take a look at number 4 here. And number 4, if you think back, we used to look at asymptotes. Well, neither of the trig functions that show up in this particular function that I'm graphing here, neither one of those has a denominator, so no asymptotes. Okay, neither one of those is rational. Now, interestingly enough, all the other trig functions that we've got, all the other 4 of them, cotangent, tangent, cosecant, secant, they would all have vertical asymptotes in them. But neither one of these do, and so the result doesn't either. Now, here's where this finally kicks in. We are looking for intervals of increase and decrease. So now here's where I got to take the derivative. So the derivative of my function, bear in mind it was, we'll go back up here, it was sine plus cosine of 2x. So the derivative of sine is going to be the cosine of x. The derivative of the cosine of 2x will be the negative sine of 2x. But I got to apply the chain rule, so I got to take the derivative of what was inside here. And the derivative of 2x is going to be 2. And instead of putting it at the back end here, I'm going to put it up front. Now, To determine the intervals of increase and decrease, I'm going to look for spots along the domain where the derivative is either undefined or equal to 0. Now, there's nowhere where this function is going to be undefined. There's fine. There's no issues here. So what I'm going to look for here is where this derivative might go to 0. Okay? Okay, well, I got a bit of a problem here because once again, I've got a trig function or a trig equation here where I've got a cosine where the argument is x and a sine where the argument is 2x. And I don't like that. I mean, I don't really like the fact that I've got two different trig functions in here. But I really don't like the fact that this is the cosine of x and this is the the sine of 2x. And so I'm going to go and grab an identity here. Sine of 2x is the same as 2 sine x cosine of x. Well, I like that a lot better. Okay? I'm still not thrilled with the fact that I've got a cosine, well, two cosines now here, and a sine of x. It'd be better if they were all in terms of the same trig function here, but this is much better. Mostly because what I can do now is factor out a cosine. Okay, I've got a cosine common to those two terms here, and so this will become 1 minus the product of those two, 4 sine of x. Okay, so now I've got two different trig functions here that I can solve. Okay, I've got the cosine of x. If the product here is equal to 0, well, it might be the cosine that's equal to 0. Now, between 0 and 2 pi, cosine will go to 0 at two different angles, at pi over 2 and then at 3 pi over 2. So that's going to correspond to 1.6, and I should be putting approximately here because I am rounding, and 4.7. Here, sine is going to go, sine of x is going to be equal to positive 1/4. Sine is positive in quadrants 1 and 2. So I would find the reference angle and then I would put the reference angle into those two quadrants. And in this case, what we're going to get here is 0.3, okay, and 2.9. Now, what's significant about those points here, okay, is that these are the points, these are the values of x where this function goes to 0. Okay, where its value is 0 here. So we know that the function is going to be increasing, okay, on either side of these. So what I would do here normally is I would put out my number line here, and I would identify the different values here, starting at 0 and ending out here at 2 pi. Okay, so if I put these in order here, what have I got? I've got this 0.3 first. And then I've got this 1.6, 2.9, and then I've got this 4.7 right here. My spacing's not great, but that's okay. What I'm really interested in here is what is going on with the derivative inside these intervals here, between these numbers. Okay, because now not looking at the 0 and the 2 pi here, but at these numbers right here, the derivative goes to 0. Whether it's positive or negative will indicate to me whether the function's increasing or decreasing. Now, and this is again work I've done prior to this. I've already gone through and investigated. And I know that if you pick a number between 0 and 0.3 and plug it into the derivative, you are going to get a positive result here. In this interval, it will be negative. In this interval, that result will be positive. This will be negative. This will be positive. And so that corresponds to intervals of increase and decrease that look like this. But we got to be careful here. Okay, we got to be careful when we write this out here. So that's why I'm going to go over here. Okay, my function is increasing. Okay, it's increasing on the interval from 0 to 0.3. Now, bear in mind, this is a rounded value here. Union 1.6 to 2.9. The union 4.7, and I'll put up to 2 pi here. Now, notice that I'm including the endpoints here. That's just something that I have chosen to do, and I know this is consistent with with a number of resources, but not with all resources. There will be lots of people out there that will say that no, that's not true. Okay, the derivative is positive on the open interval, and that I agree with 100% because you're going to see a lot of people use parentheses here. The derivative is positive on the open interval, but I believe that means that it's increasing on the closed interval. So I would argue that this is now decreasing, and I would put closed intervals here between 0.3 and 1.6, together with, what do we got here? What was it? 2.9 up to 4.7. Okay? So those are my intervals of increase and decrease. Now, the next thing that I'm going to look at here is going to be my max and min points. And that is actually very easy for me to do right now. I just have to look at my graph here. Sorry, my graph. That's what I'm building here. I just have to look at my intervals here. When I've got an x value that's shared between an interval that's increasing and decreasing, I know that that's either got to be a maximum or a minimum. So if I go from an interval that's increasing to one that's decreasing, the shared endpoint must be a maximum point. So my maximum points are going to be these. Okay, I already know it's going to happen at 0.3. Whereas if I got another one here, another endpoint here of an increasing sequence is going to be 2.9. Okay, and then I know that this increases up to 2 pi. So at the end here, I'm going to have a maximum here at 2 pi. So, and that's going to be an endpoint. So bear in mind that this is going to be an end point there. So my maximum here, when I go to my calculator and plug that in, you're going to find you're going to get a 1.1. When you plug 2.9 in, you get a 1.1. So there's a little bit of symmetry there. It looks kind of nice. And if you plug 2 pi in, turns out you get 1. My minimums are going to be points that are the endpoints of decreasing sequences and the beginning point of an increasing sequence. So I can see that 1.6 falls into that category. Figure that out in a second. And I believe I've also got 4.7, the end point of a decreasing sequence, beginning point of an increasing sequence. Okay, and then because the x value 0 is the beginning of the leftmost, okay, the leftmost interval of increase, that's also going to be a minimum. Now, I know it's an endpoint again, okay, and I'll put that up here. This is an endpoint. And I would call this up here, this maximum here, this is going to be a left-handed max, and this is going to be a right-handed max. If you plug 0 in, you're going to get 1. And let's go through to these other ones here. If I plug 1.6 in, turns out you get 0. And 4.7, turns out you get -2. So here we go. These are points that we can plot, and we'll start to connect the dots here. We know that these are going to be the maximums, these are going to be the minimums here. These two are going to be right-handed, left-handed maximums and minimums because they're endpoints. All right, now, what's next will be concavity. This is going to require me to take the second derivative, okay? Now, let's flip back here. Bear in mind that my first derivative is the cosine of x, and my second derivative, the other part of that is going to be -2 sine of 2x. So when I come here and take my second derivative, that is going to be negative sine of x minus 4 cosine of 2x. Now bear in mind that there was a 2 out front there, but remember I'm going to take the derivative again using the chain rule, so another 2 is going to pop out. So that's where that 4 comes from. I'm interested in finding the endpoints where this increasing and decreasing of the derivative changes here. So I'm going to set this equal to 0 because that will correspond to, if you want to think of it this way, maximums are minimums when the derivative or the slope is changing, my maximum slope, my minimum slope. I got to solve this equation. Again, I don't like the fact that I've got a sine function here and a cosine, but the bigger issue is the x and the 2x here. So this is the one that's got to go. And just like I did a few moments ago, I'm going to replace the cosine of 2x with 1 minus 2 sine squared of x. It's a really handy little identity there. So let's now multiply this thing through. Negative sine x minus 4 plus 8 sine squared of x. I'm going to move the terms around just to make this 8 sine squared of x minus the sine of x minus 4. I just like it better when it's in that order. Now I want to factor this, so I'm looking for factors, the negative 4 with the 8 there. When I look at this, I'm not 100% sure that I can factor this. So what I'm going to do is just off to the side here, I'm just going to check the discriminant here. I'm going to check the negative, b squared minus 4ac. Well, b squared, the b value here is negative 1, so b squared is going to be 1 minus 4 times 8 times negative 4. Okay, well that's going to be, what have I got here? It's going to be 1, that's going to be 32 multiplied by 8. That's going to be 128. That's going to end up being positive 129. Okay, that's not a perfect square root, so it turns out I'm not going to be able to factor this. But because it's positive, there is a solution. So it turns out I'm actually going to have to use the quadratic formula to solve this, which is actually a little bit awesome. So the sine of x is going to equal negative of negative 1 plus or minus the square root of, and I've already figured that out. Thanks to that discriminant that I was just using, I already know what that is. So that's kind of a nice thing. Then multiply by 2 times a, and a value here is 8, so the denominator is going to be 16. Okay, so this is just going to be 1 plus or minus the square root of 129 over 16. Well, I told you before that I had already gone through and done a bunch of these calculations here. So there are two options here for what sine could equal, and I'm going to have to look at both of them. So, and I've already gone to my calculator here. So on one hand, sine could equal, and I'll put this out here to 4 decimal places, 0.77, what have I got here, 24, or sine of x could equal negative 0.6474. Those are the two values that I get here to 4 decimal places. Here, sine is positive, so positive in the first 2 quadrants. I would do the reference angle, and then I would put those 2 reference angles in the proper quadrants here. Turns out I'm going to get 0.9. Again, this is approximate. And what's my other one? 2.3. Here, sine is negative. That occurs in quadrants 3 and 4. I would do the inverse sine of 0.6474 to get the reference angle, and then put those in the proper quadrants. Quadrants 3 and 4, so it's going to be 5.6 when I add pi to that, and then when I subtract that reference angle from 2 pi, I will get 3.8. Oh, sorry, I did that backwards here. Sorry, this is subtracting it from 2 pi, this is adding it to pi. Sorry, I don't know, I have no explanation as to why I would have flipped those and done the larger one first. Not really thinking here. But anyway, I hope what I'm doing here to go from here to here makes sense. That's been covered in a lot of detail in other videos that I've done where I look solely at the trigonometry. Remember, the purpose of this lesson here is to just walk through a curve sketching example with trigonometry. So this is kind of a secondary issue here. Now, when I plug these into my number line here, okay, starting at 0, ending at 2 pi, and plugging my numbers in, what have I got here? I'm going to start with 0.9, and then we're going to move to 2.3, 3.8, and then 5.6. Just like I told you before here, I've already gone through and done this, so I'm picking numbers in each of these intervals here. If I plug those numbers into my second derivative, I'm just going to get 0. I mean, that's the whole point of what I just did here. It's what's happening in between that's important. So if I grab numbers in between there and go back up to my second derivative, and I've already done this, you're going to get a negative here, a positive here, negative here, positive here, negative here. Meaning that this is going to be concave down, concave up, down, up, down. So I would say that this function, or this graph here, is going to be concave up on the interval, okay? And I will go from 0, concave up 0.9 is what I meant to say, because it starts here, 0.9 to 2.3, union 3.8 to 5.6, and it's going to be concave down on the interval. This is actually where I was mentally starting a couple seconds ago here. Actually, let's see if I can clean that up just a little bit. Nope, doesn't want to. All right, wow, that doesn't want to come off at all there. That is a little frustrating. So this will be 0 to 0.9, union 2.3 to 3.8, union 5.6 to 2 pi. Okay. Now, the very last thing that I'm going to do here is I'm going to look for inflection points. Now, normally, I have to really be careful because I'm looking for points where the concavity changes. But it turns out this is all kind of already done for me. I've already quite clear that all of these points that I found here in the previous step here, they were all inflection points. So I can actually enter those into my calculator and get them. So my points are 0.9, 0.6, 2.3, 0.6, some symmetry there, 3.9, or 3.8 I think is what I had there, 3.8, my mistake, negative 0.5, and 5.6, negative 0.5. So those are all my points of inflection. Now, finally, when I get to the bottom here, and actually I am going to just fit my graph right in here. Okay, my graph's going to look something like this. And let's put the x-axis right here. And maybe this is what have I got here? If I make this, I'll make this 1 to -1, -2. So when I do this and plot my points here, and I'm just going to do this relatively quickly. What I'll do is I already know what this looks like, so I'm going to plot the points. Once you do this, you get to see here pretty quickly that this is just connecting the dots. Okay, in this one here, I've got that x-intercept here. This is going to drop way down to here with the point of inflection there. Comes back up, intercept, and then this is going to hit at 2 pi. Well, it was 1 again. And so you can almost just see the graph being drawn here. We just got to make sure that we make the curve here. So following what's happening here, okay, if you go back to my, for example, my intervals of increasing and decreasing here, what you get here is that it's increasing here, decreasing here, it's increasing here, decreases to here, and then increases to here. Okay? And then my concavity, and there's a break there, it's going to be, what did I say? It was going to be concave down here, and then it's concave up till about in between here and here, these two. In between here and here, it's going to be concave down. Here to here, it's concave up, and then towards the end there, concave down. Which actually makes perfect sense when I plot the graph here. Maybe I'll change colors. So it's going to be increasing and concave down. It's going to be like this. Concave down to here, then changes to concave up to there. Concave down and increasing is there to my maximum. Concave down and decreasing, there's my point of inflection. So now, moving down and concave up. I could have done that better. Oh boy. Up through that point of inflection here. Then it's concave down and then it's increasing. That's a little uglier than I was hoping it would be at the end here, but that's what that particular function would look like, roughly.